Hi, this is a live stream for 9ENF for physics. And I see I've already got some people here, so go ahead and let me know, yeah, who you are. Say hello. And once we get a bunch of you here, we're going to start up for the day. More on lenses and finding objects 3 ways. So let me turn my phone off so we're not disturbed. Voila. I got 3 already. Thanks for joining in. So I got Felina and Benedict, hello to you both. So we'll check for each of you. Dynamite. Who else I got? I got Christian. I got Tony. I got Magdalena. Wow. All right. Coming quick. Christian, Magdalena, Tony. And more. Kira is here. Noah Berry is here. Nicholas is here. Larissa's here. Great. While we're having others join, here's a little warm-up question for those already here. Can you draw the shape with parentheses of a converging lens? And I'll write down others. I got Lucy here. I've got Natalie and Malin are here. I've got Lucy and several of you got it already. Nice. Good job. That is indeed correct for a converging lens. Whoa, very good. Okay, I better write down Lucy is here. Good. Good. I got some others. Wow, you guys are quick. I got Emily is here. I got Marilyn is here. Good. Okay. Another question. What is a medium to warm up while we're taking roll? What is a medium when we're talking about light, I guess, or optics? Noah Delps is here. What is a medium? Hope we had that word. I had it with my 10th grade, and I thought I did it with you guys too. Let's find out. It's not like small, medium, or large. Ah, Magdalena has it. Super. So it is indeed the material that light travels through. Okay. How about some others? Can you give me some examples of a medium? Ah, Julian L is here. Good. How about some examples of different mediums? Christian says glass. So does Noah and Natalie. They are right. Noah Delp says water. That's right. A prism is a medium. That is also true, Tony. Water, says Marilyn. Plastic, says Natalie. Yep, that's true, like contact lenses. Several of you have plastic, and that's right. Yeah, good. Still going to wait about 1 more minute, and then we'll start up for the day. But we're getting close, and I've got 20 of you, so let me know when you arrive. Ben Defty is here. Great, man. Still have some others from last week that I hope can make it again this week. I got a new whiteboard, but I'm using the old one because I still have our stuff from last week. So we're going to pick it up from here. And I'll just tell you what our goal is for the day. All right. There are 3 ways to find the distance to an image. The image is what comes out the other side when object goes through a lens. And we're going to show you that physically. I got it set up over on my desk to show you. We're going to use a formula, and the third way is a diagram. Okay, now before anything else though, I looked over your homeworks and they look pretty good for the most part. The only problem is a lot of you screwed up the first diagram. So I redid it. I'm going to hold it up and I'm going to do it on the board here. And what you need to have for that first diagram, I got something like air, I got water, but the angle, folks, the angle has to go closer to a vertical line. The vertical line, I'll draw it on the board. The vertical line, oh, and I got some new markers, so hope that works better for us today. So here we go. What I'm talking about is this. I'll erase this in a second. So when you did this thing with, let's call it air and water, then the light comes in at this angle. We measure that angle with this line. This vertical line is called the normal line. But when it comes out the other side, it's then closer to the normal line. So it's going to be something like this, okay? So when light refracts or bends, like we talked about last week, it's going to go closer to the normal when it's a denser medium, okay? So obviously water is denser than air. I say this because on the homework, some of you had it backwards, and it was wrong. So this is the right way on your homework. It's like the first page or two I assigned from the book where you're supposed to draw a diagram like that. Okay? All right. I think most of you here are going to be here. And so we'll go ahead and start up for the day. I'm going to leave that. I guess I'll leave it up here. I got the lenses again that people were showing me. So there's the converging lens, right? Or convex, as they call it. And the other one, again, is a concave lens, or we saw it in diverging lens. Good. Micah's here. Thank you, Micah. Anybody else here? Okay. Others can say hi when they join. Let's go back and see where we left off last week. Okay, so if you weren't here, you want to get those notes from that last diagram. I'll kind of explain what's going on. We're going to do this today with an actual candle. So here's going on. I got a candle. That's my object. And we're going to measure the distance from the lens. This is supposed to be the lens. From there over here. That's called DO. So DO is distance to the object. Let's see if you can see that. That's a little hard to see. Okay, so DO. So it's distance to object. And then I got DI. And that's going to be the distance to the image. The image is going to land on the screen over here. Screen or image. You may wonder, what the heck does it mean by an image? I'm going to show you one, so don't worry. Okay, so that's DI from the middle of the lens to where the thing lands over here. We're going to see what it looks like on the lens. If it was a candle, then somehow I'm going to have something here representing the candle. But we're not going to draw that till we come back. Okay. All right, screen for the image, lens, and last time we talked about every lens has a focal length. And I think we measured one last time. I kind of did this, and then when it got real sharp, I could measure the focal length. But we did that already. So what we're going to do today is we're going to do, I think I'm going to erase this now. I'm going to put my books aside for who's here and who's not. And Leah just told me she joined, but she can't type. Okay, wonder if she heard her hand. All right, so Leah's here. Welcome, Leah. And let's kind of continue. Okay, so essentially, I'm ready to talk about our objective for the day. I knew that would happen. Stay. Okay, here we go. Our objective is to learn 3 ways to find the distance to an image. Santiago's here. Good. Three ways to find the distance to the image. In other words, DI. Okay? 3 ways to find the distance to the image, which is called DI. Now, essentially, you guys are all going to be my lab partners, all right? I'm going to carry the laptop over here and show you my setup. I'm going to turn out the lights, at least mostly, and then I'm going to show you, and we're going to do some measuring together. I need you guys to write some stuff down. I've got the candle, I got everything. I just don't have any way to write it over there while I'm holding the laptop. So you're going to have to do that for me, okay? All right, so first let me write down that I got Sarah here. Let's see if I got anybody else joining me. Sarah's not here. Good. Before I walk over there with you, let's see. Santiago, could one way be to measure the length of the image and the length of the lens? Yeah, the focal length of the lens. That's right, Santiago. So we're going to do that as well. You might have learned that. Somehow use an equation. Good. So those are the 3 ways. Yeah, essentially we're gonna physically measure. That'll be our first way. I tell you what, you can get ready for me, all right? Because I'm going to need you to fill in some stuff. So we're going to fill in the D, O, the distance to the object. We're going to find the F, the focal length of the lens. It's written on there, so we're just going to write it down, okay? Now we're going to measure DI, the distance to the image, okay? I wish you were here to do that with me. Okay, anybody else here before I walk over there? Anybody else new? Okay, all right. Okay. If you come, just sign in. I'll write you down later. Okay, you ready? Here we go. This is the weird magic of whatever. I'm gonna turn off the lights. Okay, you're up and running. Follow me. Don't get dizzy. I got you. There's our setup. Okay, so let's get some of the stuff out of the way. Let's make this a little bit better. Hey, that's not bad. Hi, you see me? Okay, so here we got, that's my screen. And here we got a candle. And I'm going to put my candle here so it's sticking up a little bit more. Can you see it? Yeah, you can see it. And here I got my lens. Okay, so the lens, it's cracked at the bottom, but I'm going to show you what it says on it. It says plus 10 centimeters. And that's going to be which thing? DI, DO, or F? What do you think? What are you going to write that one? It's in a little plastic case, but it's a converging lens. What is that? DI, DO, or F? What do you suppose that is? Give me some guesses. You got a 1 out of 3 chance. All right, I'm getting some guesses. Let's get some more. I'm getting a lot of guesses now. Unfortunately, they're all wrong. DO is not what that is. Think, what am I holding? You're getting closer. Except, what's it called, Mike? It's not called DF. It's called, Noah Barry's got it. It's F. It's the focal length. So write down the focal length for this lens. We're using the same lens the whole time, so it's just 10 centimeters, okay? All right, now you guys are getting it. Okay, hey, so write that down. Okay, so I'm going to put that here. And I'm going to light up the candle. Okay, so I'm going to turn the actual last light off. Hopefully you can still see. So here's the candle. Can you see it? Yeah, you can. It's a little tippy. Let me get it up straight here. Okay, so I'm going to measure now. And again, you're going to be my lab partner. I'm going to measure from the candle here to the lens, okay? All right, so here we go. From the candle to the lens. Whoa, it's pretty dark in here. I'm going to do it to the nearest centimeter, okay? So 16 centimeters. And that's going to be which thing? Which thing? D what? What's that going to be? 16 centimeters for D what? Waiting for your response. And some have got it already. Felina and Tony and others. Yes, it is DO, distance to the object. Great. Now, at the very same time, we're going to now find the distance to the image, okay? So check this out. I hope you can see that. Can you see that? Let's see. Yeah, I can't tell if you can see it or not. Maybe you can. It's like a little tiny flame. And it's out of focus. Oh, wait, now it's in focus. Now it's out of focus again. So what I want to do is I want to hold this screen and I'm going to move it back and forth till I find the right spot. I want to focus it. I want to get it in focus. You ready? So here we go. Shaboom, boom, 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 boom. Whoa, right there. Really gonna check it out? Yeah, right there, buddy. Okay, so that's where it's in focus. So now I'm going to find the distance to the image. And you can help me write this down. And it is 31 centimeters. So if you could write that down, that'd be swell. Okay. I'll put a little line. Okay. And we're going to get one other bit of data. Okay. So here we go. I'm going to put this thing at I know what I'm going to do first. Okay. It's kind of cool. You ready? Okay. This is the focal length was 10 centimeters, right? I'm going to put this thing 10 centimeters away. So the flame is right. Okay, so if I put the object 10 centimeters from the lens, and the lens has a focal length of 10 centimeters, check this out. I'm going to now try and focus that thing. And it's blurry, 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 blurry. I don't get any spot where it's focused. We're going to find out why that is together, but it's going to make sense eventually to us. So there's you won't get an image if the DO is the same value as the focal length. Okay, let's try one other. Let's put this thing at about 20. Okay, so I got this at 20 centimeters. So could you write that down, my lab partner, all of you? So the second set of data we're doing, DO is 20. And I got to focus the screen again. And there it is. Right there. That looks pretty good. And DI is 20. Well, that's weird. So they're both the same. DI and DO are both 20 centimeters. And again, my focal length, F, is still 10 centimeters because it's the same lens, right? Okay. All right. Let me look at my screen of what you've been writing. And I see some other folks I got to check in. Okay, so Alyssa, yes, you're here. I'll write you down. Anyone else that has joined us? Okay, let me bring you back to the other spot. I'm going to turn some lights on, blow out my candle before I burn the place down. Okay, here you come back. Everybody get all comfortable again. Okay. All right, so first off, let me write down my new arrivals here. Alyssa's here. Alyssa's here. Anybody else join us? I'm looking down just to take a quick look. Okay, Emily has a question. Looks like Leah does too. All right, so Emily says, so light rays originating from any point on the object will be refracted by the lens. Exactly, Emily. Good. Forming a real but inverted image. Oh, man. Doggone it. Thank you, Emily. That's what I forgot to point out to you. Did you notice that the image on my screen was upside down? And that's what I want to draw here. You ready? So on my screen, so let's do the first, can we do the first set of numbers? Okay, what was the first? Maybe somebody can list all three. My F was 10 centimeters, right? That one I know. What was my first set of numbers? Can somebody type in the DO and the DI that we measured for the first set of numbers? Thank you, a whole bunch. Okay, so I got DO 16 and DI was 31. Thanks, Tony and others. And as Emily put it, and I'm so could just kick myself because I didn't show you. Yeah, super. Thank you, everybody. On that screen, so here's the candle over here. On that screen, the candle was upside down. So it's like this. I know I couldn't see the rest of it, but if I could have, it would have been like that. So the image, here's what we say, Emily used the right terminology too. She said the image was inverted. Inverted. And inverted is a fancy word for upside down, okay? Upside down. By the way, the opposite is called upright. If it's right side up, we say it's upright. Okay, but we had an inverted image. It looked upside down when it landed on the screen. Right. Emily also said the image was real. So real is a fancy word for, if it's real in optics, it can be focused on a screen. And obviously we could. We saw it on the screen. Can focus on screen. If it's not real, and you'll know this from the computer world, it's a word that means not real and it starts with V. Can you guess what that word is? So not a real image, but a image. And that'll be can't focus. Image on the screen. And a lot of you got, including Nicholas and Kira, virtual. Well done. How are we doing time-wise? We're still doing okay. Good. So that's the scoop. Okay, so you've done one way. We physically measured what that was. I know we had some other data as well. So there was one set of data. All right, A. B, we had this weird thing where we had Noah asked, how do projectors work? Projectors enlarge the image. And I don't know if you saw that or not, but sometimes my image was enlarged and sometimes it was not enlarged. This one was enlarged. It means it was taller. And in a projector, Noah makes the image very enlarged. Super. Okay, good. And then Tony's writing the other thing where we had 20 and 20 and DI from the candle to the screen or from the lens to the screen. DI, Magdalena, is from the lens to the screen. Leia, you're all set. You're all set. Okay. If DO equals 10 centimeters and F equals 10 centimeters, we got no image. That was that case where I just couldn't focus the darn thing. We'll see why that is in a little bit. And then finally, I'm going to squeeze this in before I erase the board. The third case was if I had DO was 20 centimeters, the F was 10 centimeters, and the DI was also 20 centimeters. That's the case several of you were writing to me as well, and thank you for that. Lee is here as well. Thanks for checking in, Lee. Good. Anybody else new? Seeing if there are any things going on. Okay, so good. That's one way to get an image. I'm going to erase. Make sure you guys can see what you can see. I'll kind of turn a little bit so you can see without so much glare. All right. Okay, here we go. Let's erase, and then let's start with our second way to find the distance to an image. Okay, the second way is to use the lens formula. Okay, and I'm going to show you what that formula is. And it looks like this. It's kind of a weird looking thing. It's 1 over the focal length, f, equals 1 over the distance to the object, DO, plus 1 over the distance to the image. Whoops, DI. DI. That's a rather important thing, and I think you had it in some of the reading I had you guys do. So let's go ahead and use it. Ready? Let's check the first set of values we got. So here we go. I'm going to look back up here. Hey, I've never done this before. Ah, Amir is here. Thank you, Amir. I'm going to look back up and see what our first set of values was again. Okay, so I had 16 and 31. Okay, let's try it out. So 16. Let's do an example. Okay, so if DO was 16 and our F was 10 centimeters, I think, right? Let's use this equation. You ready? Here we go. So let's plug it in. So 1 over 10 equals 1 over 16 plus 1 over DI. Oh, I forgot to give you the question. Okay, so if DO is 16, F is 10, the question is what's DI? Let me see how we're doing on time. We're still doing okay. Good. Now, my advice for this is don't try to get some stupid common denominator or anything, okay? Thanks, Emily. But just kind of change it all to decimals if you can. So 1 over 10 is obviously 0.1. I hope you guys got a calculator. I meant to ask you to bring one next time too. And 1 over 16. Nicholas already got the answer. We'll catch up, Nicholas. 1 over 16. Is that it, Tony? So 0.065625. Can somebody verify that? Let's get the same thing as Tony so I know that we're all good to go. Others get the same as Tony for 1 divided by 16. Marilla says yes. Thanks, Marilla. Okay, good. Then it's 1 over DI. Okay, we're going to do it just like math class, not any different. I want to get this thing alone, okay? That's the thing I want to get alone. Good. Yeah, good. Thanks, everybody, for checking. So let's get rid of this other thing. So what we're going to do is we're going to subtract 0.0625, and you do that from 0.1, okay? So what is that? 0.1 minus this is going to be like I don't know, 0.0 something. Some of you got it. Let's go ahead and try it out. So 0.1 minus 0.0625. Let me know what you get. Oh, thanks, everybody. Thanks, Felina. Thanks, Sarah. So 0.0 375 sounds just right. Notice I'm leaving the labels off until we get to the end. Okay, then we'll put a label back on, I promise. Thanks everybody for checking. And that equals 1 over di. Now, you see how this di down here is in the denominator? That's a pain in the neck. So here's the way we're going to solve it. You ready? Look for a button on your calculator that looks like this. X to the minus 1 or 1 over x. Can you put that number in and then hit that button? And what it does is it gets the reciprocal, right? It flips the number upside down. So now we're going to get not 1 over di, but di. Ta-da! And we'll see if Nicholas had the right answer back at the very beginning, okay? So can you do that? It's called the reciprocal button. Reciprocal. And it's x to the negative 1 or 1 over x. Can you guys flip this thing and let me know what you get? Good. Felina's got 26.7. Let's see if others get the same thing. We do. Thank you, Marilyn, and others. 26.7 centimeters. Okay. What did let me look back here and see. Good. Everybody's getting the same thing. Thank you for checking that. Let's look back here. What did we get when we had DO at 16? We got something somewhat different, didn't we? We got like 31. Is that right? Is that what Santiago's writing there? Yeah, we got 31. Now, mathematically, this is probably the right answer. In reality, lenses are not perfect and they have somewhat defects, okay, from the glass and so on. Plus, you can probably guess me moving that screen back and forth. There's some human error there, right? Probably that is the fact as well. So if I did it perfectly, ideally with a perfect lens and a perfect human being that put the screen right at the right spot, those two numbers should be the same. So ideally that should have been 31, or had I put it in the right spot, it should have been 26.7 centimeters to agree with our work here on the formula. Okay? It should be the same. Sorry it wasn't, but that's real life, okay? Sometimes measurement, especially when I'm trying to do it on the seat of my pants here, is not always the perfect thing. Okay, let's do one more example because I want to show you in our time remaining why we had a problem. Okay, you ready? Here we go. So, Dan, I hope everybody got this, at least got the answer. I'm going to erase it, but I'm going to leave the formula. Whoa, stay put, stay there. Stop falling over. Frickin' thing. Okay, here we go. Okay, so I'll just call this, let's say example B. The other one we say was example A. Okay, so our F is again 10 centimeter. And we let our D distance to the object was 10 centimeters. Okay, you ready? Plug it in. Let's see what happens. Hope Emily says, moving an object closer to the focal point results in the image becoming further and further away. Yes, you're right. Exactly. Okay, so here we go. Drop these suckers in. 1 over 10 again equals, man, mentally screwing up here. Equals 1 over 10 centimeters plus 1 over di. Okay, so 0.1 equals 0.1 plus 1 over di. So we're going to subtract, right? 0.1 from each side. And I get 0 equals 1 over di. All right, well, let's just keep going. Let's keep going. So what did we do last time? We did this x to the minus 1 button. Can you try that? Or 1 over x. What do you do if you get 0? What happens? So can you try that? You catching up here? So if those are the same, like our second case, then we subtract from each side. I get 0 equals 1 over di. Go ahead and put 0 in and do 1 over x. And now the last case we did, Santiago, was do was 20. We did this one, or at least I want to do this one now before we run out of time. Okay, so what's di? So 1 divided by 0. Benedict says it's not a number. Sarah says it doesn't work. You're right. So the math, then we say what? It's undefined. And what can we say about our di? Do you remember what happened? What happened when I had it at the same math failure? Exactly, Lee. What happened when I had the distance to the object the same as the focal length? What happened when I tried to move the screen around and get an image? It didn't focus. Exactly. Thanks, Ben and others. Great. Yeah, it was blurry. So, aha. Mathematically, that's why we couldn't get an image. So that's why we got no image when DO equaled F. It just doesn't give you an image. Why is that? We're going to find out next time. We still got a couple minutes, but I'll just let you know. Next time we're going to do that, and life will be good. Okay, the third example. I may start it and have you guys do it as a little tiny bit of homework. So I'm going to erase this. I'm going to leave that because I know you might still be writing. Okay, so we still had 10 centimeters. And this time we put it at, that's the one, Santiago, you were referring to, 20 centimeters. Yes, I know we're running out of time, but we're going to have just enough time to do that. Question, can you let us know when the next meeting will be? I'll try for a week from today. I don't think I have to go to school, but I'll try for a week from today. What's the exact difference between DI and F? I'm going to have to wait to answer that, Magdalena. Okay, so. Okay, so here we go. So if I got 1 over 10 centimeters equals 1 over 20 centimeters plus 1 over di. This one we can kind of do in our head. So I got 0.1. 1 divided by 20 is 0.05. So let's now subtract 0.05. And I got 0.05 left equals 1 over di. And I'm rushing here because I know we're almost out of time. And so my question is, can you guys kind of catch up a little bit and find this now? Depends on your calculator which of these you got. The x to the minus 1 or 1 over x for 0.05. And let me know what is di. Thanks for answering each other's questions, Benedict and Magdalena. That's great. 20. Aha! Okay, so here we learned something else. So second aha. Aha! When the DO equals 2 times the focal length, then, so when DO equals 2F, then DI equals the same thing. That was 20, and our answer for DI is also the same distance, 20 centimeters. Interestingly enough, and I think Emily said this earlier, it would be flipped. So if that's our candle, then the image would also be 20 centimeters away, but it would be inverted, it'd be upside down. It'd be upside down. Whew. Thank you for joining me today. If you haven't said hi yet, please do, so I mark it as here. Thanks everybody for participating. You can guess what we're going to do next week. We're going to use the third way, which is diagrams, lens diagrams. You practice this a little in the book. We'll do it together next week. And call me if you got, or write me if you got questions until then. Okay? Assignment is still coming to you. Bye, everybody. Lena, which Lena are you? Lena Satar or Lena Zink? Lena Zink. Yes, I got you, Lena. Okay.